So this is project 2212, and we're going to go over the final stuff today, give you the status where everything ended up. So if you look at the background, the project was initiated back in May of 2012. It was basically $1 million over 2 years. And from our standpoint, the key thing was setting in the statement of need. And it was a little bit different how SERDIP attacked this than maybe other funding agencies and other projects throughout our industry. The two major things in the statement of need. One was a long-term tin whisker mitigation. Come up with a coating. Let's talk about a coating that stops whiskers, that reduces the threat that whiskers has to our electronics. But the more interesting thing from our standpoint, and I think that's unique in the industry, is the project, the statement of need asks for the coating should be a tool to alter whisker mechanisms. How do they initiate? How do they grow? What can we do to stop some of the fundamental things that we know about whiskers? And rather than just being a mitigation of coat and cover them, let's go impact that side of it. I'm on cell 2. I'm going to go to cell 3. And Rockwell's approach is to look at a family of materials called alkali silica glasses. And one we have been using, as I'll talk in a couple of the other cells, we've been using the ASG, or I call it liquid glass, in some other systems, so we thought it was applicable to whiskers. And more importantly, the properties of liquid glass, the ASG coating, they can change how moisture goes through surfaces. They're very tailorable, and we felt that it was a system that offered some advantages to how we could impact tin whisker formation and growth. So if you go to cell 4, from our technical approach, if I put my engineering hat, or I put my scientist hat on, say, what do we need a conformal coating to do in terms of how it protects our electronics? One, or maybe more importantly, what do I want out of a coating that changes whiskers' behavior? One of the things would be, can it stop moisture? Can it alter the corrosion of tin oxide? And SERDIP is a couple other projects going right now with Dr. Steph Meshner and Dr. Polina Signovsky looking at corrosion. And they've made some really neat discoveries and findings with their results showing that moisture and whiskers, there is a relationship there. So any coating that's going to impact whiskers has to dealing with corrosion. A coating ideally would bond to the outside layer of tin in the tin oxide. Being bonded would change some things around, especially having a whisker initiate and form. You'd like the coating to be tailorable. So do I want it rough? Do I want it smooth? Do I want it to have less stress, lower, higher stress? What can you change in the coating that could then impact whiskers? And of course, I want to be able to deal with the coating in terms of its deposition thickness and its coverage. If it's a great coating, but I can't get it down in a repeatable, consistent thickness, I'm in trouble. Or if I have trouble getting it to have good coating coverage consistency, then it's not the most ideal thing to work down. If we go to cell 5, put my engineer's hat on. I'm out on the factory floor building electronics. One of the things I want my coating to do is I want a high modulus, I want a high hardness. So if a whisker does initiate, it's going to have a tough time working its way through the coating. And again, SERDIP also has some sister projects to the project I'm presenting today. Dr. Steph Meshner and the gang are working with putting particles in coating. And so this project looks at one method of slowing down whiskers, and SERDIP has a couple others that both look like they're going to yield some things. Whatever coating I have, it really has to be able to cover the complex surfaces of an electronics assembly. Electronics assembly have a lot of skyline, got a lot of X, Y, and Z dimensions. I want to be able to coat the edges of leads, behind the leads, areas that where whiskers might initiate and grow. Number one, and I get beat up by my folks here at Rockwell all the time, don't create some process that's some special, unique, we've never seen it before. I want to go out to my typical factory. I want to be able to use typical temperatures. I want to be able to cure it in conventional ovens. I don't want to have to go buy a $3 million machine that this is all it does. Of course, the factory folks, they want short deposition times, short cure times. They're looking at their process cycles. And then, of course, last, want to be able to rework this. So That's kind of the wish list from a science or a engineering perspective. If you go to cell 6, so we put a team together, and this team was folks here at Rockwell Collins. We also included the folks at the University of Maryland, and I'll talk to further slides what Dr. Mike Osterman's been able to do in terms of metal vapor arc, or MVA. And then real critical to what we believed to the project was we needed somebody other than Rockwell doing this. Cool, if Rockwell can do it, that's neat. But if you can't transition this out to the industrial base, then you might as well not done the work. And so we teamed up with folks at Plasma Ruggedized Solutions. They're an industry conformal coat provider to the defense industry and aerospace. And they were one of our other key partners in terms of looking at commercialization of the coating. If we go to cell 7, a little bit on liquid glass or alkali silica glass, ASG specifically, kind of a very nice material. We've been using them for a couple other things, other products, but you can control the deposition rates. They're highly tailorable to what you want to do. They also cure, and essentially when I say cure, these are coatings that are based on a water solution, not solvent solutions, so you're driving off the water. But it happens at right around 120, 125 degrees C, and those are temperatures we see in the factory every day in terms of curing other types of adhesive materials, so that wasn't a shock to the system. We know that the liquid glass will work in electronics. We're using it right now on some temperature issues where you're trying to do a lot of heat transfer. You can put diamond particles into the liquid glass, and it allows for a lot of thermal type applications. So we thought that's why we proposed this material system. If you go to cell 8, our primary test vehicle for all the testing in phase 1 and phase 2 is what we call Tinman. We needed a component, or literally a component I could put in the scanning electron microscope that would not charge up, but I also wanted a component that very much mimicked and was representative of other components I find on my electronics assembly. So we essentially made a 14-pin SOIC, a small outline integrated circuit, and it's all metal. We're able to take this and coat it with bright acid tin plating. It plates very well, and bright acid tin is one of those things we know in the industry that grows whiskers like chia pets. So it made great for having a control, because if your control doesn't whisker, you don't know anything else about the other variables in your test. So if I go to cell 9, what we chose for testing as far as our conditioning of this, it was two things. One was thermal cycling, and we did just a little bit of thermal cycling. Some of the review board members looked at that and said, you know, it's a ceramic, and if we're going to take it through thermal cycle, thermal shock, we need to make sure that ceramic adheres and does what it's supposed to. So we did some standard industry thermal cycling in terms of what avionics sees, which is -55 to +125, about a 1 hour total cycle. The primary thing we subjected all the test samples to was high temperature, high humidity, 85 degrees C at 85% relative humidity. The industry has shown, and other CERDIP projects have shown, that that's a zone that really wants to promote whisker initiation and growth. And so we use that for almost all of our testing. The samples would go in and out of the chamber at specified intervals, and then were inspected using a scanning electron microscope. In industry, we use the JESD 201, so we followed that format for the most part. That does two things for us. One, it's transparent. Other people in the industry doing this type of testing could relate to this testing very well, and then they also could compare their results to the results that we would generate throughout the testing program. If we go to cell 10, I had talked about what the University of Maryland brings to it. Dr. Osterman and the guys at CALS are probably the #1 on the planet in terms of understanding metal vapor arc. Used to be that we thought that if a whisker grew in spacecraft, and of course it bridged two circuits and caused a short, in the vacuum of space, we could then create a plasma. And a plasma is not a real good thing for electronics. They don't handle it very well. Well, through some testing that the University of Maryland had done, we found that that can happen. It isn't exclusive to a vacuum environment. So what we wanted to do was include Mike on this in terms of what we could see what would twice do with some of the coatings. So I'll walk through some of his results briefly. but very interesting. I think Mike killed 2 or 3 grad students doing this, but he actually took whiskers and we glued real actual whiskers across 2 electrode surfaces to create the test specimens. And I'll talk about some of those results, but some very neat things we were able to learn out of the program. Of course, last but not least is the guys at Plasma Ruggedized Solutions. Whatever we came up with here in terms of using equipment, could they replicate, and would they have any suggestions on improvements? And we use a standard system, the Semtech Spectrum S820. We use it in our current operation, spraying conformal coatings. It's a widely used piece of equipment around the industry. So that got us back to being away from some specialized type of thing. If you look at the program overall, we split it into 2 phases, each phase being 1 year. Phase 1 was some pretty heavy developmental, looking at the material, getting the initial formulations of liquid glass and seeing how they performed. And then phase 2, we left ourselves a little bit of a window to try taking what we learned in phase 1. Do we need to change the formulations, improve the formulations? And then in phase 2, as you'll see on further cells, we got into building real assemblies. I'm a big one on testing widgets, but widgets don't tell you the real thing. We felt you needed to get out on the production line and try some things. So that's what we're going to cover in phase 2. And you can see in the graph here, we've tried to highlight each of the partners where they worked. Primarily in phase 2 was PRS and Rockwell, and Maryland and Cal's folks, University of Maryland, was in phase 1. So if we go to cell 13, one of the first things, of course, is taking the liquid glass, looking at these ASG materials, and let's make sure we run a design of experiments, stick to the science in terms of how should we spray it, what kind of pressures, what's the height of the nozzle off a board, what gives us the best spray parameters. And these graphs are a little bit of an eye chart, but you can always blow those up at your leisure. And you can see we're able to determine several things. One, our pretreatment. It'd be nice if I didn't have to pre-treat a board, but we did show that we needed UV ozone or even some plasma, but primarily UV ozone to prepare the surfaces. We're spraying the liquid glass on a standard circuit board, so you're seeing plastics, you're seeing metals, you're seeing solder mask, a number of organic and inorganic things, and the UV ozone just promoted better adhesion for what we wanted to do. We also learned that to really control our thickness, we had to watch our barrel pressure and our co-flow pressure. And we found a number of interactions we make sure we controlled as we sprayed. If I go to cell 14, once we had our spray parameters down, we decided what are we going to do in terms of data. So here's our Tinman specimen, and our phase 1 test board had 4 Tinman per test board, and then we had 9 boards in the chamber, and we went in, and every 500 hours of exposure we would pull out a specimen and we would look at it under the SEM. And you can see here we had 5 different measurement areas. 4 of these measurement areas are on the lead bends, which is where you tend to see whiskers. And then we also measured area 5, which is out on a flat. In phase 2, we actually quit looking at area number 5 here, mainly because no whiskers were growing. And from our industry work, of course, where the lead is bent, when it goes lead forming, down here you can see that's the high stress area, and that's where we saw most of the whiskers initiate and start to grow. We also did a second set of boards based on some discussions with Dr. Steph Meshner from BAE and some of the work they're doing in their CERDIT projects. We kind of teamed up. We wanted to see, one set of these specimens was every 500 hours going in and out of the humidity chamber. We'd take them, look at them in the SEM, put them back in the humidity chamber, but that's about 24 hours of exposure. Did coming out of the chamber change the behavior? So we had a set of specimens that we pulled out, we inspected, and never went back in. So those were staggered such that we would accumulate 500 hours, 1,000 hours, 1,500 hours, trying to look to see if any differences there. When we did look at these specimens, and we got down to looking at each of the 5 areas, we would go in and measure 3 different areas on here randomly. It's a 0.125 millimeter diameter, and we would measure lengths and measure whisker density. And that's how we were tracking what was happening between the different variables in the design of experiments. To go to cell 15, When we started into this, based on the early work looking at the materials, we picked two different types of liquid glass or alkali silica glasses. And you'll hear me talk about these ASG4, which was a little more ductile formulation, the way that the team looked at it. It didn't put as much stress into the substrate it was sitting on. And then we also looked at ASG5. And ASG5 was a little more stressful coating, but ASG5 also gave us better environmental robustness. Oxygen, moisture, things would not move through it, diffuse through it nearly as readily as ASG4. So it gave us a kind of two different angles to look at that. And what we found out real early, and I hope it shows up in your PowerPoints, but on the right here, this is ASG5. And you can see it's crazed. It has a lot of cracks in it. And what we found is the ASG5 was causing, it was too stiff. It was causing cracking. The cracking, it was then generating stress into the bright acid tin coating underneath. And the whiskers just thought that was great. They just grew like crazy, and especially early on, if you look at the graph. We had more whiskers on our ASG5 than we had on our controls. Versus the ASG4, and it's a lot less of a rigid coating, it's less stress, and we didn't see nearly the behavior that we're having with the ASG5. And that was nice. Some of the science we were putting in, and we were seeing differences in how you can formulate the composition of those coatings, and it ends up that both formulations perform better than the control, but in the end, the ASG4 coating was doing much, much better. One of the other things, and here's the aha moment that we had in phase one. I very naively, being a material engineer, thought, I'm going to shut these coatings down and they're never going to whisker. And that wasn't happening. And if you think about it, tin, zinc, and cadmium all grow whiskers. They're known whisker growers. And for me to shut down a basic material or elemental characteristic, not only is silly, you could call it stupid. But what we found, and thank goodness our co-ops, when they're working on this, young minds do some neat things. They looked at it and they looked at these coatings. And you can see here on the right the ASG5 coating. The whiskers grow through this, and they grow through this like chia pets. They're just everywhere. But they're really short, and they look like little button mushrooms. As opposed to the whisker behavior here on the left we were seeing on our control specimens that had no coatings. They were growing long whiskers. We talk about them as blades of grass, long enough that they could go short. Versus my little button mushrooms, they're not going to short to anything anywhere. And so this was our big aha moment, that our coatings, while they couldn't shut down whisker initiation, they clearly could change the behavior. So if I can make them short and they grow lots of them and then stop growing, that was more of a win-win than just completely shutting down whiskers, which in 2020 hindsight, you're not going to change an elemental characteristic. If we go to cell 17,
if I could
go ahead,
back,
do that.
Yeah, I just have a question on graph 15. If you could go back just a moment, and I want to capture it now because I think with that graph up there. So when you're at 4,000 hours, I know what you're saying with regard to ASG5, that it's saturated, and that's why it levels off at a certain number of whiskers. But you also see ASG4 sort of catching up and surpassing. So what's going on ASG4 in that realm when you're at 4,000 hours?
Yeah, very good question. What we looked at is while ASG4 didn't crack nearly as readily as ASG5, it started to crack later on. And so as the coating develops those stress cracks, which you can see real well here in ASG5, that allowed the environment, the moisture and high temp, high humidity to get down to that surface. So we end up with the same type of whiskers. It just was a delay compared to ASG5. And what that told us is we need to make sure our formulation is more towards the less stress type of coating than the right side. One could, I suppose, debate and say, hey, we got to the same place, so maybe having ASG5 and its environmental robustness being higher than ASG4 is a good thing. But I think we have more control in here if you look at ASG4 compared to ASG5. So it's a matter of both coatings ended up in the same place. They just had different time phases to their behavior. They ended up doing the same thing.
And it may be more important to know the type of
speak up, Nate, so they can hear you.
The type of whisker, I think, is probably not apparent in that plot either. Like Dave showed in graph 16, the coatings make the whiskers grow in a different way. They're more like mushrooms versus blades of grass. So the existence of whiskers can mean different things depending on how they're growing.
Yeah, and that's Dr. Nate Lauer. Nate's our guru on the coating and how we play with the different compositions within the coating.
With both 4 and 5, you get the mushroom type of growth.
Yeah, we get the same type of behavior. They just their progression to get their changes and how they interact with the environment is a little bit different.
Okay, thank you.
And we weren't expecting that. So again, some of the science we learned along the way, we thought that was pretty cool. Okay, I'm going to jump out to cell 17. The other thing we had said in our proposal we really wanted to play with is a lot of nanoparticles going into coatings, into different adhesives and coatings today is really showing some neat science. And so what Nate wanted to do is we put some coatings in. Again, this is just a summary cell. If you go back and look at the annual PowerPoints we put together, there's a lot more detail. But what we found is that if you put nanoparticles into both ASG5 or ASG4, it actually is better than just having the coatings without particles. Again, the ASG5 tended to produce whiskers faster than the ASG4. But what we found was thicker coatings are better than thin coatings, and coatings that had 10 nanometer sized alumina outperformed a 40 nanometer sized zinc oxide. In the phase 1, we looked at alumina and zinc oxide, and the alumina did much better than the zinc. And some of that could be just zinc versus aluminum, but as you'll see in a couple of more slides, we really think the particle size was playing a much bigger role than the elemental particle itself. The other thing we made sure we included in here is looking at the conventional coatings. And we had both Parylene and we had acrylic. Those are two big primary coatings the industry used. And what we noticed is that both these coatings had fewer whiskers initially than a lot of the coating variables we looked into. But what was going on is the whiskers are growing under the coating. And with our measurement technique, I didn't count a whisker until I clearly could define it as a whisker. So they really had to grow and poke up through the coating before, when we measured, we said it counted as a whisker. And you can see here on the right on cell 18, this is a whisker that it hasn't quite completely penetrated out of the coating. There's still an acrylic coating over the top of it, but it's worked its way out. So by the first couple thousand hours, of course, the conventional coatings looked better than anything. By 4,000 hours, everybody got up towards what our controls were showing. Little tough time looking at Parylene. Parylene's a very uniform coating put down by vacuum deposition, but even with the Parylene, we got to that point. I think what was more encouraging was the samples coated by plasma ruggedized solutions had the same behavior as the samples that we coated here at Rockwell. So someone using the same machine but a different facility, different state, completely away, independent coater of sorts, we ended up in the same place. One other thing to report on a phase 1 was that the thermal cycling. We did 1,500 total cycles. That's what's called out in the industry specifications. And again, that was minus 55 degrees C to plus 125 degrees C. And that was about a 1-hour cycle. It's truly thermal cycle, not thermal shock. So we transition at less than 10 degrees C per minute. So even after 1,500 hours of this, which is roughly about 3 months of continuous cycling, you can see here on the photograph, there are some cracks that showed up, but they're very slight. In fact, there's less cracking than what we saw after 500 hours with the ASG4 coating, and way less than we saw with the ASG5 coating. So we wanted to prove that we couldn't spall this coating off, that it was well adhered to the leads, the metallic leads on the components on the plastic. And after, we didn't do any more thermal cycling after we finished this. We put all our efforts into the high temp, high humidity testing. One of the things that the Surge Up project allowed that we did not see in the industry which will seem kind of silly, but we wanted to confirm the obvious. So what you see here on the right side is the guys at the University of Maryland, Dr. Mike Osterman. Here's the electrodes, and I talked about we would bridge an electrode or a whisker across the electrodes. So this electrode has no coating on it, and they use silver adhesive, conductive silver adhesive, to bond a whisker to it. The right side on this electrode, we put acrylic or parylene or the ASG coatings on. And then what you would do is you would bring the electrodes in contact, so this whisker is now making contact with this side of the electrode. So when Mike applied 50 volts, if it could conduct, it would go from this electrode through the whisker to this electrode. We never had any electrical connections. We never had an arc initiated. And that's important because we wanted to see if you had a metal surface that grew a whisker and it grew onto a surface that had a liquid glass coating or an acrylic coating or a parylene coating, what would happen? Because a lot of people in the industry use that as a mitigation. We were able to, during the testing, during the program, show that you are getting mitigation, that a whisker doesn't just touching the surface. It has to grow through this surface and make metal contact. So somewhat obvious, but that data didn't exist in the industry. Now it's out there for other companies to use. The other thing, which was much, much trickier, we learned just how well FedEx handles packages. What Mike would do at the University of Maryland, he would attach a whisker to this side of the electrode, and he would attach a whisker to this side of the electrode. He would then ship those samples to us here in Cedar Rapids, Iowa. We would spray coating so that we encapsulated the whisker and both sides of the electrode. So the whisker is clearly making full electrical connection. It now just has a coating over it. Our first try with FedEx was less than spectacular. They broke all the whiskers, so we had to put together something they could play football with. But eventually we were successful. And what we found was if the whisker is making connection underneath the coating, and of course we did this with acrylic, with parylene, and the liquid glass, you do make an electrical connection. You do get this to spark. It doesn't escape the coating, but you could actually see the whisker glow in here as it melted. So that had never been documented in the industry. We wanted to put that out there so that people could have that in their data sets. If I go to cell 21, so at that point, well, that's phase one. We finished up. We were able to figure out which coating, what direction we wanted to go with coating. We figured out what we want to do with nanoparticles. Mike was able to do things at the University of Maryland looking at metal vapor arc, and the guys at PRS were able to replicate and show some improvements and things we were able to talk back and forth. In phase two, we said we're done with widgets. I want to take a board. I want to go fabricate a board and do this. So we took the Sabre board. This is a board you can purchase from Practical Components, and we populated it. They're dummy components, but they're standard components from Amcor, who's a big supplier in the industry. And we're able to build this out on our line in our Coralville facility just like any other electronic circuit board. And the one thing that was really nice is if you look down here in the lower image, there was an SOIC with a standard component, but on this test board, there are two positions for this SOIC. So we actually took our Tinman, tape and reeled them, and so when we put this one down, we didn't put its twin sister. We put the Tinman in place of what would have been a plastic component there. So on our card, what we took to our SEM for analysis in phase two, we were able to look at Tinman again. We were able to look at a commercial SOIC, and then we were able to look at a commercial QFP. The reason this was important is, of course, Tinman is going to do everything it did in phase one. But phase two, when you solder, you tend to get a lot of solder up on these leads, and it self-poisons the lead. It's one of the mitigations the industry uses. And that way, we didn't expect to see any whiskers on this because of soldering. This quad flat pack, you can imagine, solder doesn't run all the way to the top of the leads. The leads are too tall. So we thought we might have a chance to see some and record some whisker behavior at the top of the lead. So this part, we built the boards. We had 100% yield. We built 120 test vehicles. And then we carefully came out. We had these routed so you could snap them out of here, and that became our test vehicle for phase two. And in phase two, we did the same thing, 85-85. We did full 4,000 hours. But in this case, we pulled things every 1,000 hours rather than every 500 hours. and we did not do two different sets. We just put everything in, and after one set had accumulated 1,000 hours, we pulled it out, never to go back in. The next set accumulated 2,000 hours, we pulled that out. And then what we did is we came in and looked at these parts. Now,
David, can you tell me about how these were soldered? Was this like one of those wave systems, or?
Good question. I should have covered that. This board is all surface mount technology. So this board went into the standard solder paste stencil, and it was stenciled on each of the pads. Tin lead solder. We kept with the tin lead process. Then a pick and place machine would put each of the parts down on its location, and then it went through a reflow oven. And then the boards went through our cleaning system and cleaned off any flux residues, and then they would go to the Parylene system for coating. They went to an acrylic coating cell, or they went to our liquid glass cell. And so the coatings were applied after the board was processed and cleaned. And then after coating, we then cut the sample out. We didn't remove the sample prior to the coating. We did it afterwards, trying to replicate what you would do with a real assembly going into real equipment.
So I guess we'll see the results, but I just want to ask a question. By using tin lead solder, are you stacking the cards against whisker formation?
We were here, but as you remember from phase one, the solder, this Tinman doesn't solder nearly as well as the SOIC, because bright acid tin is kind of a lousy surface to solder to. So the tops of the leads here, they were good, and I should have mentioned this too. We only soldered the four corners on Tinman. So the leads in between the four corners, there was no solder. They were not soldered down. So they weren't exposed to tin lead. So we ignored the corners and just focused on the middle.
Okay,
good point. I should have made that. I should have clarified that. I'm going to go to cell 22. What we also have built into the program is we knew that Nate had seen some other particles that we might want to try. And so we knew alumina was really good, but we said, let's try zirconia. We had some really good results with zirconia on flat samples, not on test boards, but just on glass slides. At the same time, Plasma Rare Solutions and Nate found that there was a better application head. So we had been using the 787 dispensing valve, and Assemtec came out with an ultrasonic valve, which gave much better application speed and time. And so at phase two, we kind of switched gears a little bit. We kept our phase one valve, but we looked at a new application technology, and then we also looked at a new particle. Of course, in the test, we kept no coatings for control. We did acrylic, we did Parylene, we did the liquid glass, and we did the same type of measurement, whisker length and density that I discussed in phase one. So I'm going to skip ahead one cell, I'm going to come back. We're going to go to cell 24. One thing we found out right away, we were all kind of giggly. We thought, yeah, zirconia is just going to blow the socks off alumina, and it was a miserable failure. And when we got looking in the SEM, we found out why. You can see here on the left, this is alumina, and alumina has its nice 10 nanometer particles. Zirconia, while a different particle, they were again the 40 nanometers, and you can see whiskers growing all over this creature. And the coating does not go down nearly as smooth, and so it doesn't create a surface that seals off. So while we thought zirconia would have been an improvement, it wasn't. Alumina, again, as in phase one, outperformed. I'm going to go back to cell 23, and I had Dr. Ross Wilcoxon. Ross did all the graphs on this, and I had him pull this one. The right side will tell you things, but I think the left side of the graph is much, much more telling. You can see in the yellow, those are the results for the samples that we're dealing with liquid glass coatings that contain zirconia particles versus the light blue here. That's the liquid glass that contained alumina. And you can see it's heads and tails difference, except for one coating here that didn't play very well. Zirconia just doesn't give the same benefits that alumina does. In the middle between these two blocks is our controls. And so you can see zirconia performed much worse than our controls, and the alumina did much, much better. So we kind of had to take a step back. We kind of reinvented the wheel. We should have learned, if we could have gotten a zirconia particle nanoparticle that was 10 nanometers, this might have been different. But, of course, we didn't. Our nanoparticle was in the 40 to 50 nanometer range. It just didn't perform very well. If I go forward again here to cell 24, you can see a clear difference. The alumina with its smaller nanoparticle and coming out of our spray equipment, much better than this kind of webbing, just not the same surface, not the same deposition of coating. If I jump out to cell 25, this is the data that compares how the liquid glass or the ASG coatings did against conventional, which was our Parylene and our acrylic. And sure enough, just like in before, the initial 1,000, 2,000 hours, the acrylic and Parylene are looking real good, but in the last half of the test, from 2,000 hours up to 4,000 hours, as the whiskers continued to grow, and of course underneath there, the acrylic or the Parylene do not have the benefit of having nanoparticles or being able to seal off the surface. They just don't have the same material characteristics. We know that moisture goes readily through, or moisture vapor goes readily through acrylic, and it also goes through Parylene just at a slower rate. But that moisture, once it gets down to our tin surfaces, then starts to interact and lets the whiskers initiate. And by the time we get out to 4,000 hours, those coatings were worse than the control, and a couple of our ASG coatings were performing as good or better than the controls. One of the big questions that was asked during the program was, okay, coatings look great, but we know from conventional coatings out in the industry, there's concerns about coverage. And this is a picture here of an acrylic coating on our test boards, and you can see that the very sharp edge of the toe does not retain coating, or the back side of the lead here on the picture on the right on cell 26. You can see where under black light, we have good coating out here on the solder joint and the face of the lead off the SOIC, but the back side gets shadowed, and just standard convention and coatings without taking account into that leave a problem. So what we wanted to look at is, well, how do the ASG coatings go down? And the picture here to the right, this is looking at the SOIC soldered down, and hopefully it shows up well, but there's kind of a ghosty, gray, milky look. That is the actual ASG coating. One of the advantages of ASG has over conventional coatings is it's very, very thin. It's angstrom thin. And so physics, where it says on a sharp edge, a coating is going to roll off that and not wet, it's much more in play than with thin coatings that tend to stick and stay put on sharp edges compared to conventional. The one thing we did, this picture on the lower left, I actually went in and we cut off the pads off the board. Didn't want to cut up here. I wanted to try to keep the surface intact. And what you can see here, it doesn't show up as well as I'd like, but the nice milky ghosting coating view, the observation, that's the ASG coating on the backside. So one, the coating tends to go and cover areas that conventional coatings don't cover very well. And two, because of our setup, we can spray in at different angles, and we have better spray penetration trying to come in and spray, say, at the backside or on this toe or from the top side. Just the nature of the coating lends itself to being applied with better coverage than some of the conventional coatings. Of course, Parylene is the best of all the industry coatings. Vapor deposition can coat everything uniformly. But if you're looking at, say, an acrylic or a urethane or epoxy, the ASG can do a better job of coating. It's on par, the same type of coating that would happen with a Parylene. We did one more thing I wanted to prove to myself, did I get coating down there? Because, yeah, it looks kind of gray and milky, but is that just optics, the light bouncing off it, or how good did we do? Thank goodness I have a wonderful metallographer who is very good, and he was able to take, and we did cross sections, and you can see here's the solder joint, and here's my coating over the top to protect the surface. We use kind of an outer coating of potting, and you can see the coating itself on top of the solder joint right here. Very, very thin. This was the 2 micrometer coating that we applied, and this coating is about 1 micrometer to 1.5. So when we spray thinking we're getting 2, and we do out on a flat unencumbered surface, when you get to the topography of a circuit board on curved surfaces and things that have Z height, we're getting from 1 micrometer to 1.5 micrometers. So we don't quite hit this 2, but we clearly stay above 1. If I go to cell 29, again in phase 2, working with PRS and looking at the new ultrasonic head, we're able to do some process improvements. So if you had the conventional machine that a lot of people have in the industry, and you put 4 heads on that and you wanted to spray a 2-micron thick coating, we could cover a 10 by 10 board in 12 minutes. And then, of course, it's going to be another 60 minutes to bake off the twice coating at 125 degrees C. So we were pleased with that because one of my goals was to make sure I'm in line with other conventional coating cycle times. I did not want to have to spray for an hour and then coat for an hour because industry would not be very favorable. They would look at, well, yeah, the twice coating works better with whiskers, but it costs me 2 hours of cycle time, say, than 1 hour. And we wanted to try to hit that sweet spot where when you look at transition to an industrial base, if you're more in line with what they're doing. And we were able to achieve that with the new head and doing our machine configuration. And PRS was able to do the same thing, so we were able to replicate that. If I go to cell 30, this is brand new. No one's seen this unless you've read the final report. We were able to finish up, and we still had some funding that we had not expended, so we wanted to look at the RF characteristics. Dr. Nate Lauer was doing some other stuff with RF, and so we wanted to look at this, mainly because the microwave and RF design community of the world, they can't use conventional coatings, or as you'll see from our data, we kind of think maybe they think they can't use them, but they tend not to use conformal coating because it messes up the RF signal, which tends to run on the surface of traces. And the ASG coating is so thin, we believe that it wouldn't mess with the coating whatsoever. So we had a couple different test sets here. One of the vehicles we tested up to about 12 gigahertz, and the other one we tested up to about 30 gigahertz, looking what would happen with signals in those ranges. If I go to cell 31, you'll see I'm not a Sparky, I'm a material engineer, so I don't quite understand these graphs very well, but what they tell me is if the coating was impeding the signal, you would see spikes in here. You would see differences across the signal for the different types of coatings and what we did. And for the most part, the signal without the coating and signal with the coating, they're all on top of each other. So the application of the liquid glass ASG coating didn't change how the RF signal was propagating down those test vehicles on their signal lines. We also exposed them these samples to high humidity and then really quick got them on the test vehicles or on the test rigs so that humidity didn't evaporate off. We wanted to see if we could push humidity through. And surprising, whether it was before humidity or after humidity, things didn't really change, whether it was acrylic or no coating or the ASG. So we think the RF community might have some more investigation to do in terms of coatings and what it does for their signals. We were surprised. We thought we'd see some changes, and we just didn't see any changes. It could be, too, that we need to use a different RF circuit that is more sensitive and does different things, or it could be that we need to expose it to maybe a different product use environment. But at least for the little we were able to do, we believe we were able to show some RF characteristics for both the ASG coating and just conventional coatings. If I go to cell 32, one of the things we're able to work in during the project was the folks at the it's the NPL lab in the UK. It's the UK's National Physics Laboratory. There we go. Couldn't remember the acronym. They are the British equivalent to NIST here in the U.S., and they have a very large whisker test running. They have a specimen that when a whisker, they have it electrically biased, and it's shown here on the right, so that when a whisker grows across 2 leads, such as this whisker here in this picture, if it goes and makes a connection with this lead, it will short it out. And so they don't have to put them into a scanning electron microscope. They can just plug it into a computer and let the computer do all the monitoring. And so we were able to get a set of test vehicles, and they have their own test vehicle. It's got all these little SOIC components on it. There's 24 parts per test board. We have 2 test boards in their test. They put those in, and we've gone now 12 months, right around 8,400 hours with no shorting. Their controls shorted out in the first 2 weeks. So The liquid glass coating is performing very well in their test. Also in their test, there's 31 other different conformal coat materials. Now, we don't know as much about the other materials other than their type. We know there's acrylics, we know there's urethanes, we know there's epoxy, but we don't know. Some of the members in the consortia sprayed their coatings with the intent that it's going to mitigate whiskers. Other people sprayed coatings and wanted to see with a standard process without any tweaks for whisker mitigation. So we're assuming in the next 6 to 12 months, as this test finishes up, we'll get to go out and we will publish how the ASG coating did in relationship to some more of the other standards. But we are very encouraged that we could take another test vehicle that is much easier to monitor and understand over the long term and see how it's performing. So we're pretty pumped up about this. If we go to cell 33, this is our project funding cell. This is here on the left-hand column. You can see the amounts that were authorized for Rockwell Collins, PRS, University of Maryland, and then our total funding amount. And then you can see which each of the members expended. We tried our best, but we didn't quite expend everything. There's still a little bit of money left that CERDIP will get back and can allocate to maybe someone else who's needing fundings. But there's, I think, 10 or 12K in here. But we came pretty close to being on target with how we planned the project for our expenditures and our time. Transition plan, we've got a couple things right now in motion. We've continued work with the University of Maryland and its CALS consortium, and we're putting samples into, they have a mixed flowing gas chamber, which is a hell of an ugly environment. It has NOx and SOx and chlorine and all sorts of stuff. And so we're trying to understand now with TWICE, especially the nano-filled alumina-based formulation, what it can do in terms of environmental. Will it take those type of things, salt fog, and we're working with CALS to understand on, and not on test vehicles, or on Tinman. We want to understand on electronics assembly, so we're chasing that. We're also working to find some funding. We'd like to look at vibration, drop shock, fluid susceptibility. A lot of electronics have to withstand Skydraw, which is hydraulic fluid. And then we're working with PRS to make sure that this coating would be available for anyone in the industry. If they wanted to go to PRS, they could spray it for industry applications. Conclusions, I'll let everybody read it, but in general, we felt we were very successful at showing that we found an industry piece of equipment, an industry platform, that another company without our knowledge could go and spray this coating. We didn't need any fancy process or special equipment. We were able to understand that we have the liquid glass is tailorable and that particles in it, especially alumina, is a direction to go for the future, lower stress. And our aha moment was we're not going to stop whiskers. It's an elemental characteristic. But we can change their behavior and make sure that their behavior is such they're not worried about it causing defects, specifically shorting out our electronics. And then we showed in standard thermal cycling that we're able to take the industry typical thermal cycle and the coating performs quite well. If I go to cell 36, that's our publications. We've been very active trying to publish at the IPC and SMTA organizations, their tin whisker conferences, where most of the globe comes, so we're able to try to give a lot of awareness to the coating. And then the last cell here, and we got a little bit of time for questions. As far as our social media, we're working. I just got my smartphone. I am not a social media animal. As my son says, I use Facebook. He says, just embrace the horror, Dad. So I'm not a big one on social media, but we're working with our Rockwell Collins business communication folks and finding out how we can put this out on our Facebook page and go out on our Twitter flows and publicize a little bit of what we've been able to do with the TWICE coating, that other people raise their awareness and maybe get other people start to look at it and use it. That's my last cell. I'd be happy to answer any questions someone might have.
Yeah, Dave, let me start. So we can probably help you with the social media too. And what we of course need is to have stuff that you say is publicly approved for public release. So once we're at that stage and have this ready and good to go, we'd like to help publicize that. But I also want to ask you about actual literature publications. Several of the publications, or maybe each and every one of them, was a briefing that you gave, and I want to know if there's another forum where some of the work that you've done can actually be put out in the open literature.
Yeah, absolutely. We're targeted. I think we've been asked to give another presentation, or at least potentially they're looking to ask us come back to the SMTAI conference this fall to Chicago, and they want to hear the updates, and so we're going to publish there. And they do put out a proceedings. What we are looking at is a lot of the other projects, especially talking with Polina and Steph Meshner, the Journal of Electronic Materials. A lot of people watch that publication. Steph and Polina have published there, so we're looking to see can we publish an article in there, and I believe that's going to happen here within the next 6 to 8 months, at least our submission, and get it reviewed. But we think that's of all the publications one could go to, that's the one people are paying the most attention to. There's a couple other IEEE avenues we could look at, but they're kind of siloed in the number of people that look at them, and we want to try to get as broad of exposure. So we're looking at the Journal of Electronic Materials as a publication before the end of the year.
Excellent. Our office would be very pleased to see that happen, and if you could inform us when something is submitted for publication.
Absolutely.
We would like to know about that. You mentioned early on rework, and I didn't see any comments regarding rework during your presentation. So how easy is it to take a part off and then resolder it back on and then recoat it?
Yeah, we talked about rework. We never included it in the overall project, or we were chasing other things. But of course, Rockwell and PRS have been doing a number of other things outside the project. And literally, the coating is so thin that we applied the IPC 7711 and 7722, the standard industry best practices. The coating just kind of gets out of the way. It's so thin that it doesn't burn off because it's a ceramic. But when you reflux leads and then melt the lead to, say, remove a component and solder one back down, the flux takes care of it. It carries it away. And we did a number of things where we repaired some assemblies that we could do some electrical testing, mostly just continuity, measuring resistance and ohms, and it never got in the way. So we feel real good that standard typical practices, there's no extra, no new method, no different soldering iron. You can do your standard techniques. That's not the same with, say, Parylene, which you have to use wheat starch to blast it off, or acrylic, where you'd use a solvent to dissolve it. So the advantage ASG has over conventional coatings is because it's so thin, it doesn't impede rework operations.
And then I have one last question, then I'm going to open it up and see if others do too. But my question is, do we at this point in time understand how to design for a survival lifetime, if you will? If I say I want a part to be up in space for 25 years, do I understand how to do that? Or if I say I want to put it out in the open for 50 years, do I understand how to engineer for that?
Right. My answer right now would be no. We've done some work with ASG, say, as I showed earlier, with filling with diamonds. So we have it on product out in the field, and it's holding up quite well, not having any issues. But that's one part on the board. I want to spray a whole board. I want to cover everything. And that's why we had talked about our future work. We're looking to go into the fluid susceptibility testing. What happens when I get hydraulic fluid on it? What happens when I go through salt fog? The mixed flowing gas work we're doing with the University of Maryland. We're trying to look at some more of those environmental factors to get that answer. I don't think we've got a feeling we're in the right shape, but I think I still, if I was on a 60 Minutes interview, I don't have the data to support that opinion yet.
Okay, thank you. And now, anyone else online that's got a question or comment?
Not at this time.
Okay, it's 11:59, so I think we did pretty good here. Thank you very much.